Hi there. Welcome to this tutorial, where we'll learn how to use the Smarter conventional ultrasonic flaw detector efficiently and effectively. I'll guide you step by step, from powering on the device to its basic configuration and setup. Throughout this video, we'll walk through the most important features, learn how to navigate the interface, understand the scanning process, and use essential tools that will help us get accurate and reliable inspection results. Smartor is a high-performance and versatile device designed to simplify the detection of internal discontinuities in a wide variety of materials, making it ideal for a broad range of industrial applications. Whether you already have experience with ultrasonic testing or you're just beginning to explore this technique, this guide will serve as a practical introduction to help you gain confidence and improve your skills with the equipment. We hope you find this content helpful and easy to follow. Let's get started. General specifications. Display 5.7-inch LCD with 640 by 400 pixel resolution. Units, millimeters or inches. Resolution 0.01 millimeters or 0.001 inches. Connectors. LEMO 00. Storage 16 GB SD card. Battery, lithium ion, up to 8 hours of operation. Weight 900 grams. Protection rating, IP66, resistant to dust and high-pressure water jets. Operating temperature, -10 to 45 degrees Celsius. Storage temperature, -20 to 60 degrees Celsius. Frequency range, from 0.5 to 20 megahertz. Evaluation modes, AWS D1.1, DAC curve, TCG, AVG, and Weld simulator. Device components. At the top of the unit, we find the connector cover. Turn the screw to lift the lid, and you'll see 4 ports. The first is the power input connector. The second is the SD card slot, used to store screenshots, standard parameters, inspection setups, and video recordings. The third is a mini B USB port for data transfer to a computer. The fourth is a VGA interface for video output, which can be used to connect to a monitor or projector. Finally, we have a reference block made of steel with a thickness of 4 millimeters, suitable for use with longitudinal waves. On the right side of the device, there are 2 double LEMO connectors. The first is the receiver, marked with the letter R. The second is the transmitter, marked with the letter T. And at the bottom, you'll find the encoder connector, which can be used to synchronize the on-screen scan with the physical movement of the transducer during an inspection. At the back of the device, you'll find the battery compartment. To access it, loosen the screws and gently lift the cover. Next, remove the battery to insert it correctly. It's important to make sure the terminals on the battery and the device are properly aligned. Once everything is in place, reattach the cover, ensuring the tabs fit securely into the housing slots. The battery provides around 8 hours of operation, although this may vary depending on screen brightness, color scheme, and general system settings. When the battery level is low, the device will shut down automatically to prevent deep discharge. Once the device is powered on and the UT mode is selected, we enter the main screen. We'll begin by reviewing the icon layout and the A-scan display. In the top left corner, you'll see the battery status icon. In this example, it shows a full charge. Each bar represents 25% of the total charge. If the device won't be used for a long period, it's recommended to power it on at least once a month and remove the battery. The next icon confirms that the VGA video output is active. Following that, the SD card icon indicates that the card is properly inserted in the device. At the center top, you'll see the date and time information, which can be adjusted through the System Settings menu. Next is the icon that shows the type of transducer connected. This could be a straight beam probe, like the one in use now, or if a dual-element probe is connected and activated, the icon will change automatically. Lastly, we have the alarm icon. If the circle is black, the alarm is deactivated. If it flashes red, the alarm is active. The top bar also displays key measurement data. The first value is the current gain in decibels, followed by the amplitude in percentage, the depth, the surface distance, and the total distance the ultrasonic signal travels to reach the reflector. These readings are linked to the gate setup and the selected measurement units. The value at the bottom of the bar represents the base gain plus any tracking decibel compensation. At the center of the screen, we see the A-scan waveform. The horizontal scale represents the travel distance of the ultrasonic signal. In this example, the distance is set to 10 inches. Each division equals 20% of the total range. This distance can be adjusted using the range function. The vertical scale shows signal strength or amplitude in percentage, from 0 to 100%. Each division also represents 20% of the total value. Finally, at the bottom of the screen is the main menu, and on the left side, you'll find the functions related to each submenu. Let's now review the physical controls and function keys on the Smartor device. At the bottom of the front panel, we have the power button used to turn the device on or off. Next, we find the F1 and F2 keys. These are user-defined shortcut functions. Currently, F1 is set to auto 80% amplitude, meaning that when pressed, the echo is automatically adjusted to reach 80% of the screen height. F2 is set to freeze the screen. When activated, the freeze icon appears in the top right corner. These shortcut keys can be reassigned from the System Settings menu for other specific functions as needed. The next button is used to save data. It allows you to store a screenshot, save the current parameters as a standard setup, or save both the screenshot and parameters together. You can also use it to record a video or access stored files. The Home button takes you back to the main menu or exits a submenu after making a selection. Just below, we have the quick access keys for gain and gate. The gain key allows you to quickly increase or decrease the decibel level. The gate key enables you to adjust both the start and height of the detection gate. Finally, the navigation arrows let you scroll through menus. The up and down arrows move between functions, while the left and right arrows adjust their values. Pressing Enter confirms the selection or opens the desired submenu. Device menus. Let's now go over the main menus available on the device. These are divided into 3 main sections. First menu. Here you'll find the primary settings for the ultrasonic system and the test piece. This menu includes access to the basic configuration, where you can adjust the gain step increments, inspection range, and gate settings. You can also set up alarms that trigger based on defined parameters. In the pulsar receiver submenu, you can configure voltage, pulse width, damping, PF, and enable the dual mode if a dual element probe is being used. Additionally, you can adjust the working frequency of the transducer, the rectification mode, either RF or full wave, and the signal reject level. In the part setup section, you can define a default test piece by entering its thickness and material type. The ultrasonic velocity will automatically adjust according to the selected material. You can also choose the specific model of the probe or transducer in use, including its technical parameters. Finally, from this menu, you can adjust the A-scan display, activate image freeze, and customize the on-screen layout. Second menu, 2 of 3. This section allows you to make standard adjustments, such as velocity calibration, probe delay using 2 known reference points, refracted angle calibration for wedge inspection with angle beam probes, DAC or TCG curve generation, and setup of additional evaluation curves like DACA, third menu, 3 of 3. In the final section, you can activate a previously configured weld profile for inspection, transducer position, and ultrasonic beam path. Now we'll begin with the preliminary setup. In the basic submenu, we will make the following adjustments. Gain step, 0.5 decibels. Range, 5 inches. Screen delay, 0. Gate measurement mode, peak. In the transmitter-receiver submenu, configure. Voltage, 150 volts. Damping, 50 ohms. Pulse repetition frequency, PRF, 150 Hz. Dual mode, off. Filter, select by bandwidth or by the transducer's center frequency. For this example, select 2.5 MHz. Rectification, full wave. In the Part/Probe submenu, set the following. Piece thickness, 1 inch. Material velocity, 0.2320 inches per microsecond for longitudinal waves. Transducer model. In this example, we'll use P2.5 to 20L. Once selected, the instrument automatically recognizes the transducer's characteristics. If you're using a transducer not listed in the system folders, you can create a new one with the required specifications from the Probe Manager menu. Lastly, probe delay, 0 microseconds. Finally, in the Auto Calibration submenu, you will find 3 calibration options. First, probe delay. The instrument calculates the probe delay using a single known reference point. 2. Velocity. It calculates the material velocity based on the propagation time difference. And 3. Velocity plus probe delay. This is the most commonly used method and involves a 2-point calibration. You'll need 2 known references. In reference 1, enter the lower value. In reference 2, enter the higher value from the reference block. It is important to note that the values of these and other settings may vary depending on the test conditions and the type of material being inspected. Therefore, equipment configuration may differ from one application to another. For this straight beam calibration, we'll use a Type 2 IIW reference block and a 2.5 MHz transducer. In the Auto Calibration submenu, we'll enter the values for the 2 references. Reference 1, 1 inch. Reference 2, 4 inches. Place the transducer in position G on the reference block. Move the gate until it intercepts the first echo corresponding to 1 inch. Press F1 to set the reference echo to 80% amplitude. Then navigate to the Save function. And press the Enter key to record the first reference. The gate will automatically shift to the position of the second reference. Now place the transducer in position E on the block. And press Enter again to record the second reference. Once the distance calibration is complete, the instrument will display 2 values in the upper right corner: the probe delay and the calculated material velocity. Finally, verify the reference values. 4 inches and 1 inch. With this, we complete the straight beam calibration process. Now we will perform the calibration using a dual-element transducer. We will use the same configuration previously used with straight beam. Activate the dual mode in the Transmit-Receive submenu. Set the filter to 5 MHz. Select the transducer model, which in this example is the TJM5-10CL, with a frequency of 5 MHz and a 10 mm diameter. Now go to the Auto Calibration submenu, and we will perform the calibration using multiple echoes. The first reference is 1 inch, and the second reference is 2 inches. Place the transducer in position G on the calibration block. The gate must be placed over the first echo. Press the F1 key so the amplitude reaches 80%. Then press Enter on the Save function to store the first reference. Now move the gate to the second echo, corresponding to 2 inches, and press the Save key again. Once the calibration is complete, the instrument will display the velocity and delay values of the transducer. Verify that the distances are correct. 1 inch and 2 inches. With this, we complete the calibration using a dual-element transducer. Custom transducer. When using a transducer that is not preloaded in the device folders, we can create a new one. Press the Home key. Select the type of transducer. Go to the Manage menu. Then create a new entry. Select the Probe submenu, either Straight Beam, Angle Beam, or Dual. In this case, I'll select Angle Beam. You can set the desired angle, for example, 70 degrees. The system will automatically update the value of the angle tangent. Next, select the frequency, 2.25 MHz. Choose the shape of the transducer, round or rectangular. Then adjust the size of the crystal contact area, 0.625 by 0.625 inches. Save the transducer configuration and assign it a name. For example, AWS 2.25. Press the Home key to finish. And finally return to the detection menu. We will now perform the preliminary setup and calibration using an angle beam. In the Basic submenu, we make the following adjustments. Gain step, 0.5 decibels. Display range, 10 inches. Display delay, 0. Gate measurement mode, peak. In the transmitter-receiver submenu, we configure voltage, 150 volts. Damping, 1000 ohms. Pulse repetition frequency, 150 Hz. Dual mode, off. Filter. Select a bandwidth that covers the center frequency of the transducer. In this case, for a 2.25 MHz transducer, select a range from 1 to 4 MHz. Rectification, full wave. Reject, 0%. In the Workpiece transducer submenu, thickness, 4 inches. Transducer model. For this example, we select the custom transducer we created earlier, AWS 2.25. When selected, the system automatically updates the material velocity for shear waves. the K value, which is the tangent of the angle, and allows you to enter the X value, which is the distance from the sound exit point on the transducer to the front edge of the wedge. In the Auto Calibration submenu, we select Velocity plus Probe Delay Calibration. Reference 1, 4 inches. Reference 2, 8 inches. Now we are ready to perform the angle beam calibration. According to the reference code to be used, some requirements will be necessary for the calibration, which we will describe below. AWS D1.1 calibration requires verification of the index point, distance calibration, angle verification, and sensitivity calibration. We will begin with the index point verification, the exit point of the beam. Place the transducer in position D, aligning the wedge marking line with the notch on the block. Move the transducer back and forth until you find the maximum amplitude of the echo corresponding to the 4-inch radius. Once located, press F1 to bring the amplitude to 80%. Verify that both reference marks align. If the wedge line does not match the notch on the block, draw a new line on the wedge. That will be the index point of the beam exit. In that same position, press Enter on the record function to store the first reference. At 4 inches, and then the second reference at 8 inches. Once the calibration is complete, verify that the measured distances are 4 inches and 8 inches. With these steps, we have completed the distance calibration. Refraction angle verification. We will access the Angle Calibration submenu and verify the ultrasound beam path angle. 2 reference values must be entered. The first is the depth of the hole, which we will use for verification. The depth is 1.2 inches. This is the value we must enter as reference 1. The second reference corresponds to the diameter or aperture of the hole. In this case, 2 inches. Place the transducer in position B for angles from 40 to 60 degrees, or in position C for angles from 60 to 70 degrees. For this example, we will use a 70-degree angle, so we place the transducer in position C, aligned with the 70-degree mark, facing the hole with a diameter of 2 inches and a depth of 1.2 inches. Move the transducer back and forth until you find the maximum echo amplitude. Once the maximum amplitude is found, go to the Calibrate option. And confirm by pressing Enter to save the angle. In the upper right corner, the corrected angle will be displayed, as well as the K value, which corresponds to the tangent of the angle. The permitted tolerance is plus or minus 2 degrees, as established by the AWS D1.1 code. It is important to enter the hole values, depth, and diameter, according to the transducer position. We will now continue with the sensitivity adjustment from the AWS menu. Place the transducer in position A. Move it back and forth until you obtain the maximum echo amplitude corresponding to the 0.6-inch diameter hole. Once the maximum amplitude is found, adjust the decibels, either increasing or decreasing, to bring the reference echo amplitude between 40 and 60%. In this case, we adjust the decibels to set the height to 50%. Press Enter on the record function to store the sensitivity setting. Finally, on the left-hand side of the screen, the discontinuity classification will be displayed. With this, we complete the AWS calibration. One of the features of the instrument is that it allows us to create DAC curves to establish the relative size of a discontinuity. We will now perform the distance amplitude correction curve. According to the thickness of the weld to be inspected, first, select the thickness of the block. For this example, we will use a basic ASME block with a thickness of 1.5 inches. Previously, we performed the distance calibration using a 5 MHz transducer, half-inch diameter, and a 70-degree angle. Select the curve submenu. Position the transducer toward the hole located at 1/4 of the block thickness. Place the gate over the echo corresponding to the 1/4 T-hole. And move the transducer back and forth until you find the maximum amplitude. Once the maximum amplitude is found, use the gain control to increase the decibels so that the echo from the hole reaches 80% amplitude. When it reaches 80%, press Enter in the record function to store the first point. Now aim the transducer at the hole located at half of the thickness, half T. Place the gate over the echo and move the transducer until you find the maximum amplitude. Without changing the gain control, press Enter to save the second point. Finally, aim the transducer at the hole located at 3/4 of the thickness, 3/4 T. Place the gate over the corresponding echo and move the transducer back and forth until the maximum amplitude is found. Once located without adjusting the gain, press Enter again to store the third point. We can continue creating more points by locating the same holes at 3/4 T, half T, and 1/4 T, but now using the second leg and an extended ASME basic block. The number of points on the DAC curve will depend on the weld thickness and the ultrasound travel distance to ensure full coverage of the weld bead. Once the DAC curve is complete, we can create additional curves to establish different sensitivity levels. Enter the Curve Control submenu. Two curves will be automatically generated, one at +6 decibels and another at -6 decibels, representing a discontinuity half the size of the reference level. We can draw up to 5 additional curves. For this example, we will add one at -14 decibels, representing a 20% sensitivity level. In the type function, we can also change the shape of the curves, either linear or curved. We've concluded the creation of the DAC curve. If we want to save a file, we press the Save key. We can save a screenshot, the configured parameters, a screenshot with parameters, or a video recording. We can also manage previously saved files. For this example, we will save the DAC curve by pressing Enter on the parameters function. At the bottom of the screen, a message will appear indicating that the file has been saved, and a name will be assigned to it automatically. Now we will restart the instrument to demonstrate how to load saved files. Press the Home key and select System Settings. Choose the default option and press Enter. The instrument will reset to factory settings. Next, we enter the detection menu and load the previously saved file. Press the Home key and select Manage. In the submenu, select Storage. In the Type function, press Enter. Use the right arrow key to select the desired file. And press Enter again to open it. All previously configured parameters will be automatically loaded. Finally, press F2 to unfreeze the screen. A visual aid provided by this instrument is the simulation of the weld profile. This tool uses a function called dynamic beam tracking, which allows the user to determine the location of discontinuities within the weld. To create a profile, press the Home key. Select the Manage option. In the Workpiece submenu, select New. Choose the joint type. Up to 14 different weld profiles can be configured. For this example, we will select a Y joint. Now we modify the base material thickness, 0.40 inches. Select the material type. And adjust the workpiece dimensions. These values can be taken from the WPS or the fabrication drawing. We begin with the crown width, 0.575 inches. Then the root face height, 0.090 inches. The root opening, 0.100 inches. The reinforcement height, 0.060 inches. The root reinforcement height, 0.025 inches. And finally, the heat-affected zone, 0.120 inches. Once all the dimensions are set, press Enter on the Finish function. And assign a name to the weld. Press the Home key to save. Then return to the Detection menu. In the Transducer Workpiece submenu, select the workpiece we just created. Navigate to the Weld Simulator submenu and activate the simulator. Once the simulator is visible, turn on the function color by number of legs. Then enter the X value, which is the distance between the beam index point and the front of the wedge. Return to the Simulator submenu. When performing an inspection and a discontinuity is detected, enter the surface distance as the E value. With this information, the simulator will display a red indication showing the location of the discontinuity in the weld. As an additional information, it is also possible to activate the number of beams in the simulator. We've completed the optimal handling of the Smartor Ultrasonic Flaw Detector.